Gauss's law is one of the most powerful equations in electromagnetism, but knowing the equation isn't actually the hard part. The hard part is being able to recognize when you should actually use Gauss's law. Hopefully by the end of this video, you'll be able to recognize the four main patterns of Gauss's law. The four patterns are spherical symmetry, cylindrical symmetry, planar symmetry, and conductors. Once you're able to recognize all of these four patterns and which one you should be using for your problem, almost all of Gauss's law problems will become simple for you. First pattern is spherical symmetry, and the easiest example of this is a point charge. The electric field has to point radially away from this point charge, and the only thing the magnitude of the electric field is going to depend on is the distance r from the point charge, and each of these electric field lines are all a distance r away from the point. So you can say that there's a circle or a sphere around this point charge, and every point on this point charge is going to have the same magnitude of E. So this sphere here with the radius r is our Gaussian surface. If you have a point charge, your Gaussian surface should be a sphere, because the magnitude of E only depends on the distance from the charge, and everywhere on this sphere is going to be the same electric field. And what this means is the electric field is actually constant. And since it's constant, you're able to pull it outside of the integral in Gauss's law. So what this would look like is Gauss's law on the left-hand side simply becomes a surface integral. Now the surface integral of a sphere is just 4 pi r squared, and then you add the right hand side of Gauss's law, and the charge enclosed is just this one point charge, so it's just Q, and then you can rewrite this whole expression to solve for E. And it's as simple as that. So the trick here is not that spheres are some special trick when it comes to Gauss's law. Spheres are useful because everywhere on the sphere the electric field has the same magnitude, which means you're able to pull it out of the integral and turn the problem basically into an algebra equation. Now for the pattern of cylindrical symmetry, instead of this point charge, say you have an infinite line of charge. Again, the electric field has to point radially away at all points on this line, but there's also a length component here, and in this case a sphere wouldn't work, so the next best option is a cylinder. So for this, your Gaussian surface would be a cylinder. But you have to be careful. Something that we didn't have to think about in our last problem is the electric field isn't perpendicular to the surface at all points. On the curved surface of the cylinder, it is perpendicular to all points. On the end caps of the cylinder, the electric field is parallel. So what you should note is that when the electric field is perpendicular to the surface, it's not zero, but when the electric field is parallel to the surface, it would be zero. So any electric field contribution on these circle parts, the end caps of the cylinder, does not contribute to the system. So now that we know that, we can solve the Gauss's law equation. Again, the electric field is constant at all points, so you can pull it out of the integral. And what you're left with is another surface area integral, which for a cylinder is just 2 pi RL, where R, again, is the radius of the cylinder, and L is the length of the cylinder. And in this case, you have the line charge, so the charge enclosed in this cylinder is the line charge times the length of the cylinder. So plugging this all together, you can again solve for the electric field. So the electric field doesn't depend on the length of the cylinder at all, only the radial component. So again, notice that we never had to integrate over where all the individual charges were on this line charge. Symmetry turned the entire problem into an algebra problem by choosing a surface where this electric field is constant, allowing us to pull it out of the integral and having just a surface integral, which is simple for these shapes. The third pattern is planar symmetry, which is an infinite sheet of charge. And in the case of this infinite sheet, the electric field is going to point perpendicular upwards or perpendicular downwards because there's no preferred direction along the surface. The Gaussian surface for this situation is what's called a pillbox. It's a cylinder that goes through this plane where the circles on the ends of the cylinder are parallel to this plane, and the curved surfaces are all parallel to the plane. So it's basically the opposite of the last symmetry we saw. In this case, only the circular part of the cylinder has a contribution from the electric field because that's where the electric field is perpendicular. And anywhere on the curved surface of the cylinder, the electric field is going to be parallel, so that would contribute nothing. And again, the Gaussian surface used here is what's called a pillbox. So now that we know which parts of the Gaussian surface contribute from the electric field, we can solve Gauss's law. Again, the electric field is constant, so you can pull that outside the integral. And what's left is the area. Well, the area is just these circles on the cylinder. And we can just use a shorthand saying that the area of each of these cylinders is just A. Just keep in mind that there's two of them. So then this becomes the electric field times twice the area. And again, the charge enclosed is the charge density times the area. Bringing this all together, we can again solve for the electric field. And you'll notice something, again, the area in this case cancels out. So the electric field is simply sigma over 2 epsilon. And another interesting thing is there's no r in this equation, unlike the last case with the cylinder symmetry. So the electric field of an infinite sheet doesn't decrease with distance. This fourth pattern isn't really a shape, it's more of a physical condition. The first thing is that the electric field is 0 inside of conductor. So in the case of the arbitrary conductor, we can use a pillbox again. And because the field inside is 0, the pillbox across the surface gives us a direct relationship between the surface charge and the electric field immediately outside. And by that I mean electric field times the area is the surface density times the area over epsilon naught, or more explicitly, the electric field outside of this conductor is the charge density over epsilon naught. And compare this with the example before with the infinite sheet, we found this factor of 2 in the denominator. The reason that there's not this factor of 2 for conductors is because of the electric field inside the conductor. So only the top cap or the top circle of this cylinder is going to contribute. This bottom cap or whatever is inside this conductor doesn't contribute because the electric field is 0. This is a common place to make a mistake on exams or homeworks. So just make sure you're thinking about the contribution of the electric field on every surface. So this is the workflow that you need to use next time you see Gauss's law. Before you even use Gauss's law, ask, which symmetry do I have? Do I have spherical, cylindrical, planar symmetry? And once you've decided that, which direction does the electric field point? For example, for the sphere, it's only radial. For the cylinder, it's radial and lengthwise. But then you have to take into account where is the electric field parallel to the surface and where is the electric field perpendicular to the surface. Anywhere it's perpendicular, the electric field is non-zero. Anywhere it's parallel, the electric field is zero. Then you have to take into account what charge is actually enclosed. You could have tons of charges, but only one of them is enclosed in your Gaussian surface, so you only have to consider that specific charge. If you can't answer any of these questions, then Gauss's law probably isn't going to simplify the problem. It'll just make it harder for you and waste time if you're taking an exam. If you don't have spherical, cylindrical, or planar symmetry, Gauss's law is still going to be true. It's just going to be really hard to solve, and it would be easier to use Coulomb's law, which is just a direct integration. But if you have those symmetries that we discussed, Gauss's law is going to turn the entire problem into just an algebraic expression that you have to solve. So when you see a Gauss's law problem, don't start by immediately plugging into the integral. First, you have to identify your symmetry. From there, determine the direction of the electric field and choose a Gaussian surface that matches that symmetry. Then you can figure out which parts of the surface actually contribute to the flux, calculate the enclosed charge, and solve the equation. If the symmetry isn't strong enough to pull the electric field out of the integral, Gauss's law is still true, it's just probably not the easiest way to find the field. So remember, symmetry first, equation second.